We will now introduce subgroups. What is a subgroup? Suppose I have a group GO and H be a non-empty subset of G. Non-empty subset of G. H is closed under O if this holds. For all AB belongs to H, A composition B also belongs to H. Any two elements in H, this implies their composition also belongs to H. Okay, now this H together with this composition O, this is said to be a subgroup of GO if H is a non-empty subset of G, and this O is essentially the restriction that this O is essentially restriction of this O. Okay, restriction in the sense in this sense. So the restriction of O is a mapping denoted by star. Okay, it is defined only when H is closed under O. How we define this restriction star? This is a mapping from H cross H to S. H cross H to H, defined as A star B equal to A composition B whenever A and B belongs to H. So this star is called the induced composition on H. Okay, so essentially this star and this O, same thing. Only thing is we use this star when this composition is used for the when A and B are treated as elements of H. Okay, elements of H, they are also elements of G also. Okay, so this is the restriction. This is the restriction of O. Okay, now we say HO is a subgroup of GO. That means this O is essentially that star operation, the induced composition. This is star. H star is a subgroup of GO if H is a non-empty subset of G, and this star is essentially the induced composition. This star and this O is essentially same when the this star is defined in this way. Okay, we call it a restriction of O when H is closed under O. Under this condition, we can define this restriction. Okay, so subgroup means this is a non-empty subset of G, and HO also forms a subgroup. This O is restriction of this O, defined in this way. Okay, so examples, there are several examples written here. I can go through this. Improper subgroup means any group G and H is a subset, non-empty subset. This forms a group in its own right under the induced composition. Okay, now first example is suppose this is a group. Now G can be treated as a subset of G itself. Okay, so GO is a subgroup of GO itself. This is improper subgroup. Trivial subgroup, if you consider the set E, singleton E, and this composition O, this is a trivial subgroup of GO. So this is this is improper subgroup. This is trivial subgroup. Okay, if you consider Q plus, this is a group. Z plus, this is also a group. Now Q is a set of all rational numbers, Z is set of all integers, plus and minus. So this Z is a subset of Q. Okay, and this forms a subgroup of this group. Z not equal to Z is not non-empty, and Z is a subset of Q. So this forms a group of this, subgroup of this. Okay, Q plus, if you consider Q plus, this is a group. And if you consider Q star, that means excluding 0, if you consider Q star dot, this is also a group. But this is not a subgroup of this, although Q star is a subset of Q. Because this dot operation is not induced by plus operation. Okay, so operation should be same. Okay, so this is a group, this is also a group, and this is a subset of this. But non-empty subset, this is a non-empty subset of this, but this is not a subgroup of this because this operation's dot is not induced by this plus operation. Okay. Here is another example. means this is some fact. Means if GO is abelian, then HO, if HO is a subgroup of GO, then this HO is also abelian group. Okay, commutative group. This is very obvious. Okay, because this is a subset, of non-empty subset of G. So if G is commutative, every element in G commutes, then every element in H also commutes. Okay, so if GO is abelian, then any subgroup of this also abelian. If you consider S3, this is non-commutative group. A3, set of alternating group of order 3. So A3 is a subgroup of S3. And A3, mind that we have mentioned A3 is commutative. We can show that also. So set of all even permutations for a set of 3 elements. This is commutative subgroup of S3. S3 is having 6 elements. A3 is having 3 elements, even permutations. So here, this is interesting in the sense that this is a non-commutative, non-abelian group, but it has a subgroup which is abelian. A3 is a subgroup of S3 which is abelian. Okay, non-abelian groups may have abelian subgroups, but if you have abelian group, then every subgroup of it will be abelian also. Okay, now if you have suppose HO is a subgroup of GO, then identity element here and identity element here, they coincide. Not only that, inverse of any element here is same as the inverse of that element here. Okay, so if you say this is a subgroup, means this is also a group. So if the identity element is EH and here the identity element is EG, then EH and EG are essentially same. Okay, all the subgroups of this group will have the same identity element as G has. Another thing is, if A belongs to H, then its inverse in HO is same as its inverse in GO. A is an element of H. H is a group, so it is having an inverse in H. Also, this is element of H means this is also an element of G. Okay, so when you treat it as an element of G, it must have an inverse in G. Okay, so it is saying that inverse of A in H is same as the inverse of A in G. Okay, so proof is very trivial. Just apply the definition of EH and definition of EG. What is the definition of EH? Means any element you take in H, for any element H belongs to A, for all H belongs to capital H, what you have? H composition EH equal to EH composition H equal to H. This is the definition of identity EH in capital H. Similarly, if you use the definition of EG, H is an element of capital H means this small h is an element of capital G also, because this H is a non-empty subset of capital G. Therefore, if you apply the definition of EG, then H composition EG, this is equal to EG composition H equal to H. This holds for H belongs to this H belongs to capital H, because it can be treated as an element of G also. Okay. Now I can see that this is H, this is also H. So these two are same. H composition EH equal to H composition EG. And you treat H as an element of G. Now G is a group, and in a group we have seen that cancellation laws hold, left cancellation and right cancellation laws hold. So use the left cancellation. Okay, so H cancelling out, EH and EG becomes same. Okay, by left cancellation law in G, EH equal to EG. Same way, you can use the definition of the inverse to show that the inverse in H and inverse in G actually coincide for any but element H. A belongs to H. Same definition, same approach. Okay, so what we will do? Suppose A belongs to capital H. Okay, so when you treat it as an element of G, A belongs to capital H means A also belongs to capital G, because capital H is a subset of capital G. Now suppose A inverse is the inverse of A in G, and A inverse A prime is the inverse of A in H. Okay, so A inverse is inverse in A G, and A prime is inverse in H. Okay, then what we will get, use the definition of inverse. So A inverse composition A equal to A composition A inverse equal to E. EG actually, EG, NG, EG and E, we are saying that EH and EG are same, we call it E. Okay, so this is E. Similarly, if you apply the definition of A prime in capital H, you are getting A prime composition A equal to A composition A prime equal to E. Because EG and EH are same, we call it E. Okay, then you apply these two. So both are same, both are equal. So A composition A inverse, this is equal to A composition A prime. Okay, A belongs to G. A belongs to G. Okay, so from left cancellation law in G, A cancelling out, you get A inverse and A prime are same. Okay, very trivial proof. Okay, so identity element here, same as identity element here. Inverse of a particular element here, same as inverse of that element here. Okay. Now, how to check that a subset of G is it forms a subgroup? Okay. So for that we need to show two things. So here is there is a theorem. Suppose I have a group GO and H is a subset of G, non-empty subset of G. Okay. Now HO is a subgroup of GO if and only if these two conditions holds. Closure property holds and inverse also belongs to H. Okay. So to show that HO, the H is a subset, non-empty subset of G. Okay. This forms a subgroup. You need to show these two. Okay. AOB belongs to H whenever A and B both belongs to H. A inverse belongs to H whenever A belongs to H. These two. Proof is very simple. Proof is very simple. Just if you say it is a subgroup, then immediately it follows. If it is a subgroup, it is if and only if condition, right? So if it is a subgroup, you can immediately argue this holds. Statement is means proof is very simple. If it is a subgroup of GO, then subgroup of GO means if this is a subgroup of GO, then A belongs to B, B belongs to A belongs to H, B belongs to H implies A composition D belongs to H. And A belongs to H implies A inverse belongs to H. Already this is established. Okay, so if this is a subgroup, then these two conditions hold. Now the other part, if these two conditions holds, then to show it is a subgroup, you have to show all the four properties of a group. Okay, so closure property holds by this. Closure property holds by this. Associativity holds because this is a subset of this. G group means G is associative law holds here. Therefore, associative law holds here also. Okay, inverse also exists. That also follows from here. Now, identity element. Okay, so to prove the identity element, so inverse element exists by this result. And identity element, if you so a composition A inverse equal to A inverse composition A equal to E. Okay, so here if you apply this first result, A and A inverse belongs to H. It says by 2 A inverse also belongs to H. Now A belongs to H, A inverse belongs to H. This implies A composition A inverse belongs to H. That means E belongs to H. The identity element also in H. Okay, therefore this forms a subgroup. Okay, using these two properties are sufficient, necessary as well as sufficient for this to be a subgroup of this. Okay, so another way of showing this is just combination. So instead of two separately showing these two, you can simply show that A composition B inverse belongs to H. For all AB belongs to H. So that way also you can show that this is a subgroup. So the another necessary sufficient condition for a group for H to be subgroup of G is that A composition B inverse belongs to H. Whenever A belongs to H and B belongs to H. Okay. So proof, you just go through the proof, or you can derive the proof by yourselves. Okay, I'm skipping this proof. Okay, so to show that a group, so a subgroup, a subset is a group or subgroup of G, subset H is a subgroup of G, you have to show, you can show this way, that A composition B inverse belongs to H, or in this way, two property you show. Either these two you show or this one you show. Okay, so this one also you can show that if H is a subgroup of G, then this holds, and if this holds, then H is a subgroup of G. The proof is very easy. You can just go through it. I am skipping this part. Thanks. Okay. And another thing is, if GO is a group and H is a non-empty finite subset. If it is a finite subset of G, then in that case, this H forms a subgroup of G if and only if this A composition B belongs to H, holds for all AB belongs to H. Simply this showing this closure property is sufficient, as well as necessary, as well as sufficient for this finite subset to be a group. Finite subset to be a group. Okay. So proof is also simple. If this is a subgroup, then closure property holds automatically. This means if this is a subgroup, then in a subgroup this closure property always holds. Okay, so this way the proof is immediate. Now suppose this holds, this closure property holds. Okay, and we have to show this is a subgroup. Okay, the condition, extra condition here given is H is a non-empty finite subset, non-empty finite subset. Okay, so suppose this closure property holds. Okay, so closure property holds. Subgroup, in subgroup we have to show closure property, identity element, inverse element of each element, and associativity law. Okay, so closure property holds. And if the closure property holds, now H belongs to H, suppose H belongs to H. So if you keep on taking the powers, H square, means this composition of H with itself, composition of H with itself 3 times, like that. So all this belongs to H. You by this closure property, H belongs to H, H belongs to H. So H to H belongs to H, that means H square belongs to H, H cube belongs to H, like that. Now since H is finite, so this cannot be infinitely, it cannot go infinitely many times. So after some time I will get this type of scenario, H to the power R equal to H to the power S, or R less than S. It will repeat. All this cannot be distinct, somewhere it will repeat. So suppose HR equal to H to the power R equal to H to the power S, for R less than. Okay, so what we are getting from here, we are getting S minus R greater than 0 is a positive integer for which H to the power S minus R equal to E. Okay, this belongs to H. H to the power S minus R also belongs to H. So this holds means H to the power S minus R equal to E. So E belongs to H. Identity element exists. Closure property holds. Okay, and if you consider H to the power S minus R minus 1, that is essentially the inverse of H. If H belongs to capital H, H to the power S minus R minus 1. S minus R greater than 0 means S minus R greater or equal to 1. That means S minus R minus 1 greater or equal to 0. Now H to the power S minus R minus 1 belongs to capital H by closure property. Keep on taking the powers, keep on applying this composition on H itself, you get this belongs to capital H. So this belongs to capital H and small h also belongs to capital H. So by this closure property, their composition also belongs to capital H. What is the composition? Composition is H to the power S minus R. If you take the composition of this with this, you get H to the power, it should be H to the power, this is S minus R, right? So you write it properly. This is S minus R, So this should be S minus R, and that's it. That is actually my E. Okay, so this is equal to H composition H to the power R. S minus R minus 1. So you correct this value. This value is wrong written. This should be S minus R minus 1. S minus R. S minus R minus 1. Okay, so you can say that H to the power S minus R is the identity element, and for H belongs to capital H, H inverse is essentially given by H to the power S minus R minus 1. This also belongs to H. Okay, so inverse exists, identity element, inverse of each element exists, identity exists, closure property holds, associativity holds because G is a group, H is a subset. So G associativity holds in G means associativity law holds in capital H also. Okay, so this forms a group. So for finite group, to show a finite subset is a subgroup, only it is sufficient to show the closure property. Necessary as well as sufficient to show the closure property. Okay, let us prove the previous one also. Okay, so H is a subgroup of G if and only A composition B inverse belongs to H. Okay, so if it is a subgroup, if suppose this is a subgroup, if this is a subgroup, B belongs to H implies B inverse also belongs to H. So A belongs to H, B inverse belongs to H. Therefore, A composition B inverse whole inverse belongs to H. Okay, so what I am saying, I have to show these holes. Okay. So subgroup I am taking, this is a subgroup. If this is a subgroup, B belongs to H means B inverse also belongs to H because this is a subgroup, this is a group. Okay, now you take A belongs to H and B inverse belongs to H. Since it is a subgroup, by closure property, A composition B inverse belongs to H. That means this holds. Okay, so if this is a subgroup, H is a subgroup of G, then this holds. Now let us prove the converse. Suppose this condition holds. Now I have to show H is a subgroup. This condition holds, condition 1 holds. Okay, so you take A belongs to H, B belongs to H. This implies A composition B inverse belongs to H. Okay, now A belongs to H, A belongs to H. In this relation, if you take A, here A and B also you take A. So in that case, A composition A inverse belongs to H. This is EE. E belongs to H. So identity element belongs to H. Now inverse. So E belongs to H. So here you take this one E and this one A. E belongs to H, A belongs to H. So E composition A inverse also belongs to H. That means A inverse belongs to H. Okay, so inverse exists for each element in capital H, identity element exists, and closure property holds, associativity also holds. Okay, HO is a subgroup of GO. Okay, okay, closure property, I didn't prove the closure property yet. This condition holds. Closure property you can easily verify. A belongs to H. Now B belongs to H. I have shown that B for each element its inverse also belongs to H. So B belongs to H means B inverse also belongs to H. Now you apply this relation. A belongs to H. B inverse belongs to H. This implies A composition B inverse whole inverse belongs to H. That means A composition B belongs to H. Closure property. Okay, so you can show the closure property also. A belongs to H, B belongs to H. This implies A belongs to H, B inverse belongs to H. Already I have shown here for every element A, its inverse belongs to H. So for B, its inverse also belongs to H. Now you apply this relation. Okay, A belongs to H, B inverse belongs to H implies A composition B inverse whole inverse belongs to H. So this gives me A composition B belongs to H, closure property. And associativity law holds because this is a non-empty subset of G, and G's group means G's associativity property holds in G. Therefore, H also the composition O is associative. Therefore, this is a subgroup. Okay, proofs are very simple. Okay, proofs are very simple. Okay. And for finite group, if this is a finite subset, then it is a subgroup if and only you show the closure property. If and only the closure property holds. Okay, another thing is, okay, so this theorem does not hold if H is infinite subset of G. Say for example, if you take Z plus and H is set of non-negative integers. So this Z is set of positive integers as well as negative integers, and this is only positive integers. Okay, include positive, not natural number, set of natural numbers. So this is essentially a subset of these. This is essentially a subset of this, and this is not finite subset. This is infinite set. This is also infinite set, infinite subset of them. Okay, so so this n plus this does not form a group because we have a problem with in existence of inverse. If you consider 1, its inverse minus 1, 1 belongs to capital N, but its inverse does not belong to capital N. Any integer if you take, any integer if you take in capital N, its inverse, additive inverse is minus of that integer. It does not belong to capital N. Okay, and also 0 doesn't belong to capital N. So these are the problems for which this n plus it is not a group. It is close under addition, but it does not form a group because of because elements does not have their inverse in it. Inverse of 1 is minus 1. 1 belongs to capital N, but inverse, additive inverse minus 1 does not belong to capital N. So it does not form a group. Okay, so this result, that only closure property, just showing closure property, it is a subgroup. It is if and only condition, provided this subset you are taking non-empty subset, that is finite. If it is infinite, it may not hold. The example is this. Okay. Okay, so before discussing these theorems, I will give some examples. Okay, I will illustrate this subgroup with more examples. That is more interesting. I will come back to these theorems again after completing that part. Okay. Okay, here. So subgroup, some examples. This is okay. Okay, suppose consider this set of 2 cross 2 matrices, non-singular matrices. Okay, determinant is okay. Determinant is 1, not non-singular. It is determinant should be equal to 1. Okay, so this forms a subgroup of the group general linear group of order 2. Means this is the collection of all this essentially is a collection of all real non-singular matrices of order 2 with respect to matrix multiplication. Okay, so this forms, if you consider the set of all non-singular matrices, real matrices. Okay, this R stands for real, and all non-singular 2 cross 2 matrices, 2 cross 2 matrices. Okay, and you take the matrix multiplication as your operation, so that forms a group, general linear group of all real non-singular matrices of order 2. Okay, the notation already we have introduced this notation. Okay, and now I am considering a subset of this. Subset of this means 2 cross 2 matrices. Determinant is 1, non-singular matrices, but their determinant should be 1. So this actually a subset of this, and you can show this is a subgroup of this GL. And we denote this H, this determinant 0, determinant 1. The matrix collection of matrices whose determinants are all 1. Okay, we call it SL 2R. Special linear group of order 2. Special linear group of order 2. Special in the sense the determinant of those matrices are 1. Okay, so you can prove it. The proofs are given here. So proof means what will be the identity element, what will be the inverse of this element. Okay, so if you take the identity element is 1001 I2. Okay, so this belongs to this because the determinant is 1. Okay, now if you take A belongs to H, B belongs to H, determinant A1, determinant B1, and determinant AB will be also 1. That means AB also belongs to H. So closure property holds. A belongs to H, determinant A1. So determinant A inverse also equal to 1 by determinant A, that means 1. So A inverse also belongs to A. So this way you can argue identity element is this one, closure property holds, inverse of element A is A inverse, the matrix. this follows from this. A belongs to capital H means its determinant is 1. Belongs to capital H means determinant is 1. Determinant is 1 means its inverse. Determinant of the inverse is also 1. That means the inverse also belongs to H. So it forms a subgroup. This way you can show. Okay. If you consider S3, okay, set of all permutations of set of all symmetric group of order 3. Okay, so in that case you can show that this consisting of the permutations rho 0, rho 1, rho 2, rho 3, rho 4, rho 5, 6 elements. And if you take rho 0, rho 1, rho 2, it will form a subgroup of this. Rho 0, rho 3, it will also a subset and it will form a subgroup. Rho 0, rho 4, it is also subgroup. Rho 0, rho 5, it is also subgroup. Okay, so in order to show this is a subgroup, just compute the composition table. Okay, in the composition table, whatever you get inside, all are from this set itself. The closure property holds. The composition table you find, and this everywhere it is the element of this set only. Okay, not row 3. Row 3 is not in this set, so row 3 will not appear, row 5 will not appear. Okay, this also you can show that this is a composition table. Okay, so in order to show that a subset of a group is subgroup, forms a subgroup, if it is a finite set, then we have already proved that for a finite set to show it is a subgroup of this one, only the closure showing the closure property is sufficient. That means you have to just construct the computation table, and you show that all the elements in the composition table you are getting, those are actual elements of this set. So closure property, showing closure property is sufficient as well as necessary and sufficient as, for this set to be, this subset to be a subgroup of this. Similarly, you can show this is this composition table of this. So all are finite subsets. Okay, so the composition table is fine in order to establish that this is a subgroup of this. Okay, dihedral group or octic group. So already we have discussed this 8 symmetries. Consider the 8 symmetries, permutations corresponding to quadruplication of A, B, C, D. This set about 8 symmetries. So the elements we already know the elements are I, R1, R2, R3, H, V, D, D prime. Okay, so 8 elements. And you can check that these are the subsets. These are these subsets essentially, each of these subsets form the subgroup of this. So you can construct the composition table for this. So I have not computed it here. So you can check that this composition table, the composition of table this is closed. This is also closed. Closed means essentially any two elements from this set, you take the composition, then it will give an element of this set only, this subset only. Okay, so composition table shows that each of these finite sets, subsets of D4 is closed under multiplication. Therefore, each of these is a subgroup of D4. Okay, and this I is the rotation about this point O through 0 degree. R1, you know already all many times we have discussed this. R1 is rotation about O of through 90 degree. R2 is 180 degree. R3 is 270 degree rotation. And 4 reflections about means this horizontal line we denoted by H. With vertical line we denote it by V, and main diagonal we denote it by D, and other diagonal we denote it by D prime. Okay, so D4 consisting of this, and says there are means 1, 2, 3, 4, 5, 6, 7, 8. So 2 to the power 8 minus 1. That many non-empty subsets you have. Out of them, only this subsets form subgroups. 1, 2, 3, 4, 5, 6, 7, 8. These 8 subsets will form. Okay. Another interesting example is Q8. Okay. Q8, what is Q8? Q8 is the group of unit quaternions, unit quaternions. So this is there are 8 elements: I minus I, j minus j, k minus k, l minus l. Okay, what is I? I is the identity mapping, identity matrix. Okay, so 1 0 0 1, and this is minus I means 1 minus 1 0 0 minus 1. J is means in the principal diagonal it is 1 1. In the principal diagonal in J it is I minus I. Okay, and in K off diagonal it is 1 minus 1, and L off diagonal it is I. Okay, so this together with minus of this together with minus of this. So these 8 elements it forms it is actually a group, and it actually forms a subgroup of GL2 comma C. So this is a general linear group of order 2 over complex numbers. Okay, so this is the collection of all complex matrices of non-singular complex matrices of order 2. Non-singular complex matrices of order 2. Out of them, I am considering only a subset consisting of this particular 8 elements. This is Q8. It is called unit group of unit quaternions. Okay, unit quaternions. Okay, so here if you consider this actually forms a group, and this is a subgroup of this. So this is a group of all invertible complex matrices of order 2. This is a group of all invertible complex matrices of order 2. And this is a subset of all complex matrices UV minus UV bar U bar. UV belongs to C. Complex number. These are complex numbers. U bar is the conjugate of U. Okay. Now in Q8, if you consider this is a group, this is a subgroup of GL2C. Now what are the subgroups of Q8 itself? If you consider Q8, it has 4 subgroups. Okay, I minus I, J minus J, I minus I, K minus K, I minus I, L minus L. 4 subgroups. It has each will form a subgroup. Okay. And you can check that J square equal to K square equal to L square equal to minus I. J square equal to K square equal to L square equal to minus I. And if you take JK, this is giving you L. KJ minus L. KLJ, LK minus J. So JK is L, KL is J, LJ is K. KJ is minus L, LK is minus J, JL is minus K. Okay. It is if you just write the composition table of Q8, this is the composition of Q8. Q8 is having elements I minus I, J minus J, K minus K, L minus L. Okay, so if you see the composition, construct the composition table, it is along the principal diagonal, it is not symmetric. Essentially, it is not symmetric, it is not commutative. You can see from here also. KJ, JK and KJ are not same. KL and LK not same. Okay, so this is non-commutative. Q8 is non-commutative group. And as subsets, these subsets form subgroups. These subsets are formed. These subsets, non-empty subsets form subgroups. Okay. Okay, this is more interesting. Okay, the center of a group and centralizer of a group. Centralizer of an element of a group. So, what is center of a group? How we define center of a group? So, GO is a group. Okay, and we define a set H. This is set of X belongs to G such that XOG equal to GOX for all G belongs to capital G. What does this mean? This means H is collection of all those elements in G, capital G, which means X we place an element of G in capital H if it commutes with every element of capital G. X composition G equal to G composition X. This holds for all G belongs to capital G. Okay, so this is a capital H. Each element in capital H commutes with all elements in capital G. For all G belongs to capital, all small g belongs to capital G, X commutes with the small g. Okay, so this is the collection of all elements, collection of elements in capital G which commutes with all elements in capital G. Okay, so this set is called center of G. We denote it by ZG. Okay, so this is H is defined as the center of G and is denoted by ZG. And it can be proved that this ZG is a commutative subgroup of capital G. This is a commutative subgroup of capital G. Okay, so to show that this is a subgroup of G, H is a subgroup of G, what you have to show, okay, this is, it may not be finite, right? Because G may not be finite, so H may not be finite. So in that case, you cannot it is not sufficient to use that closure property. Means using only closure property, you cannot establish this fact. Okay, so what you have to do, you have to, I have shown this way. PQ belongs to H implies POQ belongs to H, P belongs to H implies P inverse belongs to H. Okay, so these two conditions I have to show. To establish that this is a subgroup of G, I have used the first theorem. Means PQ belongs to H implies POQ belongs to H, P belongs to H implies P inverse belongs to H. Okay, so utilizing this property, you can easily establish this fact. Okay, so P belongs to H, Q belongs to H. What does this mean? If P belongs to H, Q belongs to H. This implies that P belongs to H. P belongs to H means P commutes with every element of G. So P composition G equal to G composition P. And Q also belongs to H. This means Q composition G equal to G composition Q. For all G belongs to capital G. Now what we get? On both sides, okay. So P. So I have to show that Q belongs to H implies POQ belongs to H. That means POQ composition G will be equal to G composition POQ. So let us check that. Okay, P belongs to H, Q belongs to H. From here I get this relation and this relation. Now P composition Q, I take its composition with G. What is this? By associativity law, because this if you treat all these elements as elements of capital G, then by associativity law, because this is a group, we get P composition Q composition G. I can write in this way. This one equal to this one. Now Q composition G is G composition Q. I write this. Okay, now some steps are missing. So P composition G composition Q, I can write this. Now P composition G is G composition P, so you substitute that value. So G composition P, you write P composition G substituted by G composition P composition. Then associativity law, it will give you G composition P composition Q. So P composition Q, it commutes with G for all G belongs to G. Okay, so this step you complete. This is the incomplete step. Okay, so you complete this part. P composition G, replace it by G composition P, then apply the associativity law, you will get P composition G commutes with G for all G belongs to G. Therefore, P composition G is in capital H. Okay, so whenever P belongs to capital H, Q belongs to capital H, then P composition G also belongs to, P composition Q also belongs to capital H. Now, P belongs to capital H, I have to establish that P inverse also belongs to capital H. P belongs to capital H, condition, this means essentially P composition G equal to G composition P for all G belongs to G. Now P inverse composition G you take. Okay. P inverse composition G, I can write it as P inverse composition G as it is composition P composition P inverse. P composition P inverse is E. Okay, so I can write add this extra term. I can compose this extra term. Now you apply the associativity law. This is P inverse G composition P, P inverse. G composition P is P composition G. You write this. And then again you apply the associativity law. P inverse composition P, couple this, composition G, composition P inverse. This is E. That means you are getting G composition P inverse. So P inverse also commutes with G. For all G belongs to capital G. This implies P inverse also in the set capital H. Okay, so PQ belongs to H implies P composition Q belongs to H. PQ belongs to H implies P composition Q belongs to H. P belongs to H implies P inverse also belongs to H. Therefore, this is a subgroup of G. Okay, so this subgroup is called this is denoted by, this is called the center of G, denoted by ZG. It is a commutative subgroup of G. Commutativity property, I have not shown the commutativity property. You show that property. Okay, this extra property also. This is abelian group. Okay, and in case G itself is commutative group, then ZG equal to G. Okay, in case G is itself a commutative group, then this center ZG, this also, this is this coincides with G. This equal to G. Okay, one last thing I will discuss today. This is called centralizer. Let me check what I have. Okay, cyclic subgroup. Okay, many things I have. Okay, let me complete this part. Huh? Center of a group I have defined. Centralizer of a group. Okay, so centralizer of a group of an element in a group. Okay, of an element in a group. So GO is a group and I fix an element. So what is the centralizer of if you take the set H, you define in this way: set of all elements in capital G, set of elements X belongs to capital G which commutes with A. So X composition A equal to A composition X. Okay, this is called centralizer of A. Means this is the collection of all elements in G which commutes with A, commutes with this particular element A. Each element in capital H commutes with this particular element A. This is the centralizer of A. We call it CA, centralizer of the element A, denoted by CA. This is the collection of all elements in G which commutes with A, which commutes with A. Okay, so you can show this is actually a subset, non-empty subset of G. You can show this is a subgroup of G. Proof is exactly same as the center, as we have argued in showing center of a group is a subgroup. Same way you can show this thing. Okay, you take it as your exercise. You do it by your own. Okay. Okay, two more examples. I have to finish it. Two more examples. Cyclic subgroup. Cyclic subgroup. Suppose I have a group. A is a particular element. Okay. Now I take the composition of A with itself. So H is the set of all set of elements A to the power n such that n belongs to Z. So this is A square, A cube, like that. H is that set. Okay, this is having a name. This is called the cyclic subgroup of G, denoted by cyclic subgroup of G. Cyclic subgroup of G generated by A. So it is denoted by A. This angle bracket A. Okay, all elements in H are some powers of A. This is the notation of this set. Capital H is written as this: opening bracket, opening angle, closing angle A. So this is essentially each element in this set is an integral power of this particular element A in G. Now you can our claim is this is a subgroup of G. Proof is very easy. You can establish this immediately. P belongs to H, Q belongs to H. This may be infinite. Okay, so you have to show P belongs to H, Q belongs to H implies P composition Q belongs to H, and P belongs to H implies P inverse belongs to H. Okay, so how to show a set, a subset of non-empty subset is a group. This is the way you can adapt. This method you can adapt. So P belongs to H, Q belongs to H means P is some integral power of A, Q is some integral power of A. Therefore, P composition Q, this is also some integral power of A. That means it also belongs to H. Immediately you can argue this. And P belongs to H means P is some integral power of A for some integer R. So P inverse is A to the power minus R. This is also belongs to H because this is integral power. So here H I am saying this is integral power of A. And this n can be positive integer, can be negative integer. Only the restriction on this n is n must be an integer. It can be positive, it can be negative. Okay. And one point to note here that this is this set, this H, or this notation, if you denote by this notation, this is the smallest subgroup of G containing A. What does this mean? Smallest subgroup of G containing A means if you have another subgroup, any other subgroup of G containing element A, then this one is a subset of G. Okay, this is the smallest subgroup of G containing A. Any other subset of G, any other subgroup if you consider of G that contains A, then this one is the smallest. This is a subset. This is always a subset of this A. Okay, this is immediate. It immediately follows from this. You can argue it immediately. Okay. Another thing is this subgroup generated by A. This is commutative subgroup of G. This is very simple. If P and Q are in this subgroup, P is some integral power of A, Q is another integral power of A. Therefore, their composition will be this one. This is same as A to the power R plus S. This is same as A to the power S plus R. That means QOP. POQ is QOP. It's commutative. This is also always commutative. Okay. Last example is okay, some examples of the cyclic subgroups. Cyclic subgroups. Okay, cyclic subgroups. Say for I have taken my set to be 1 I minus 1 minus I. Okay, so what are the subgroups generated by each element? Subgroup generated by 1. This is 1 itself, trivial subgroup. Subset generated by I. Subgroup generated by I, the group itself, S itself. Subgroup generated by minus 1. This is 1 and minus 1. This is a proper subgroup. And subgroup generated by minus I, this is the whole set. Okay, so you have to take the integral powers of minus I. Suppose minus I to the power 0 is 1. Minus I to the power 1 is minus 1. Minus I. Minus 1 to the power square is I square. This is minus 1. Cube is I. So you get the whole. This generates the entire set. Entire set is. And this I also generates the entire set is. These are the trivial S itself. And this is one is a trivial subgroup. Only non-trivial subgroup you get, that is a subset, that is minus, generated by minus 1. If you consider Z5 plus, Z5 consisting of these classes 0, 1, 2, 3, 4. 0, 1, 2, 3, 4. So what is the subgroup generated by 0? What is the subgroup generated by 1? What is the subgroup generated by 2? You can write it. Okay, so you can see that subgroup generated by 0 is trivial subgroup. Subgroup generated by 1 or 2 or 3 or 4, all are Z5 itself. Z5 itself. Okay, so this is additive. So it will be generated by means you have to take the scalar multiple of 1. So 0 into 1, 1 into 1, 1 into 2 class 2, 1 into 3 class 3, 1 into 4 class 4. So the group subgroup generated by the element, this element is the entire group. It's same way you can show subgroup generated by 2 is also Z5. Subgroup generated by 3 is also Z5. Subgroup generated by 4 is also Z5. If you consider symmetry group of order 3, okay, so 6 elements, row 0, row 1 up to row 5. So subgroup generated by row 0, what is the subgroup? Okay, you can list down the subgroup generated by row 0, subgroup generated by row 1, subgroup generated by row 2 up to subgroup generated by row 5. Okay, so these are the you can verify this. Okay, so subgroup generated by row 0, this is the trivial subgroup. The row 0, the singleton set row 0, the identity element. This is the identity element. And other cases you get proper subgroups. Row 1 and row 2, they generate the same subgroup. Okay, row 0, row 1, row 2. And row 3 generates row 0, row 3, row 4 generates row 0, row 4, row 5 generates row 0, row 5. Okay. Okay. let us talk to them.